All right, so we're going to continue talking about exponential growth and decay. This is still part of lesson 6.7. Um, we're just going to look at kind of a new idea. So we're going to talk about what's called the growth and decay factor, and then we're going to look at the percent rate of change. These two ideas come up a lot on the Aspire test, also on the ACT. So it'll be really important to be able to distinguish the difference between the growth and decay factor and the growth and decay rate. So let's start by defining these. So the base number in an exponential equation is called the growth or decay factor. It won't ever be both, because remember our equations either represent growth or decay. So let's look at an example. Y equals like 4 times 2 to the power of x. That number that's at the base, this 2 right here, is the factor that we're talking about. And since that number is greater than 1, we know this equation would represent exponential growth. So we would call that our growth factor. All right, when modeling growth and decay, think back to those equations you were using before. We had y equals a times 1 plus r to the t, as well as y equals a times 1 minus r to the t. So when modeling growth and decay, the growth factor is defined as 1 plus r, right, since that is what would be the base of our exponential. And the decay factor would then be defined as 1 minus r. And for information, the growth and decay factor represent what we multiply each term by to get to the next consecutive term. So that's what it is, that's what it actually means and what it actually does. All right, now let's compare that to this percent rate of change. So we can use the growth and decay factor to determine the percent rate of change. And when I say percent rate of change, we're just talking about the r, the rate or the r that we were using in our exponential equations earlier. And the percent rate of change represents how much was lost or gained over time. Okay, so how much was lost or gained? Okay, so let's think about this, see if we can figure out how we would solve for these things. So for when we're talking about exponential growth, this equation that I've written is the equation that we used on question 1 of the previous section. It was 14,000 times 1 plus 0.09 to the power of t if I write it generally, and that can be simplified to 14,000 times 1.09 to the power of t if we just combine these two numbers inside the parentheses. Okay, so our first question says, what part of the first equation represents the rate r? Well, if you think back to the exponential growth equation that we were using before, then the part that was added to 1, that has to be our r. So what part of the first equation represents that? It would be 0.09. Now, the second part of this says, how could we determine the rate if given the simplified equation? So let's say that we didn't know this equation here, we never saw it, and we were just given this, 14,000 times 1.09 to the power of t. How could we determine the rate? Well, we would have to take our growth factor, which is 1.09, and subtract 1, which would give us 0.09, which is in fact the correct rate. Okay, so we took our growth factor and subtract 1. Now let's think about this same idea with exponential decay. So we've got our equation here, 18,000 times 1 minus 0.12 to the power of t. Again, we can simplify the part inside the parentheses. That would become 0.88 to the power of t. Same questions as before. What part of the first equation represents the rate? Well, it's 1 minus r. So this thing right here is r. So our rate, for our decay rate would be 0.12. Now the question is, if we didn't have this original equation, if we never saw this, how could we determine that rate? This one may be a little bit harder to see, but for consistency, we're actually going to do the exact same thing that we did before. We're going to take our decay factor, which is 0.88, and subtract 1. If we do so, we get negative 0.12. Now you may say, hey, that's negative. That is not the exact rate that we had before. But why did we get a negative here? Well, that negative right there implies decay. So it's okay, because this is a decay equation. So if we get a negative, it's okay. We would just kind of ignore the negative since we already know it's decay and say that it's decaying at a rate of 0.12. Okay, so now let's do a couple more examples and put this all together. So directions determine whether the function would represent a growth or decay exponential function, then state the rate of change. So we've got our steps over here on the left to find the rate of change. Step 1 is to determine the growth or decay factor. Step 2 is to subtract 1, remembering that a negative number indicates decay. And then we always represent rates as percents, so we need to convert our decimal back into a percent by multiplying by 100. So if we look at number 1 here, the first thing we need to do is identify if it's growth or decay. Well, if we look at the thing that is the base of our exponential, that number is greater than 1, which means this would be exponential growth. Now, to find the rate, the first thing that we do is determine the growth or decay factor. So our growth factor is that number below the exponent, which is 1.23. Next step is to subtract 1, which would give us 0.23. But again, we don't represent rates as decimals, we represent them as percents. So we would multiply this by 100. Sometimes I write the percent to remind myself that that's what I'm getting is a percent. So it looks like this equation is growing at a rate of 23%. Awesome. Let's look at number 2. So again, growth or decay. Well, that number that's the base of our exponential is smaller than 1, so this is decay. Now to find our rate, we take our decay factor, which is 0.65. Subtract 1, which gives us negative 0.35. Now, why do we get a negative? Well, it's because it's decay, right? That decay tells us the negative. And we don't want to keep that as a decimal, so we'll multiply by 100%. So this is decaying at a rate of 35%. It would be redundant to write this negative since we already stated decay, so we won't ever write the negative. We'll just say it's decaying at a rate of 35%. All right, number 3, this one's a little odd. First identify growth or decay. Well, look at the thing below the x. It's a 3. Is that number greater than 1 or between 0 and 1? Well, it's greater, so this is growth. Now to find our rate of change, we take our growth factor, which is 3, subtract 1, which gives us 2, multiply that by 100% to put it in percent form. So this one is growing at a rate of 200%. Ooh, that is a fast growing exponential. All right, let's keep going. Number 4. So this time we don't have a number in front, but that's totally okay. We still are only concerned with the base of our exponential. So we want to know if this is growth or decay. I'm not a huge fan of fractions. So I think it's easier for me if I convert this into a decimal. So 7/4 is 1.75. And that number is greater than 1, so I know this is growth. Now to find my rate, I take my growth factor, which is 1.75, subtract 1 to get 0.75, and then multiply by 100% to convert it to percent form. So this is growing at a rate of 75%. All right, two more. Number 5. To determine growth or decay, we look at the base of our exponential. 1/2 is 0.5, so this is decay. We take our decay factor, 0.5 minus 1, we get negative 0.5. We feel good about that because this is decay, so we should get a negative. Multiply by 100%, and it looks like this one is decaying at a rate of 50%. Final one, this one's a little bit strange. Because we're used to all of the ones up to this point have parentheses in them, but this 5 really is just the base of the exponential. We could rewrite this as the 5 in parentheses to the power of x, and they mean the exact same thing. So we'll solve it that way. So our base of our exponential is 5, which is greater than 1, so this is growth. To find our growth rate, we're going to take our growth factor minus 1, which gives us 4. Multiply that by 100% to put it in percent form. And it looks like our growth rate, our rate of growth, is 400%. It's moving up pretty quick. Alright, awesome. On your homework, you have a lot of problems that are very similar to this, where you gotta identify growth and decay, and then the rate of change. If you have any questions, let me know.